So here we can compare this generated as Verilog synthesized Verilog code along with the original or the actual VHDL file. So you can open this. See here this particular code is written in it's a combination of structural and behavioral programming technique. Okay, but this particular code is fully structural, and this um, all the instances are taken from the standard cell libraries, which is we have mentioned our TCL file. That means 180 nanometer technology. Okay, so this particular cell library is having this standard cells. Okay, so this is an OR gate, AND gate, okay, XOR gates, and other some components. So now we are going to generate layout by using cadence SoC encounter tool. So we are going to do that now. So for that I am going to open the tool first. So open a terminal again, then encounter. Okay, then clicking just pressing enter button. So this tools will be opened. Okay, now so the primary step is loading the generated structural Verilog code. So for that, file, import design, and you are going to choose the Verilog code which is generated. So this is integrated with all the modules. Okay, I'm adding that and close. So after this I have to mention the top module. So selecting that and giving a top module, that is manually I am selecting. So now from the library on ELF file you have to select. Okay. So that I am going to select now. So I am going to the location where I have pasted or stored this OSU library, and inside of this library I am using 180 nanometer TSMC, and inside of that this 180 nanometer LEF file I am going to select. Okay. So that's that I have selected and close. Now this place you can left blank. So here you have to select the VDD and ground. You can click on OK. So now it's loaded. Okay, now you can see the based on the information which we have provided. Okay, so this software will analyze how much instance present inside of the synthesized Verilog code. So based on that it will be automatically allocated a core area. Okay, so this allocated a space here, so you can measure. So how much is the core area now? See here, you can, by using this you can. So it's having around 349 micrometer length. It's a square. Okay, so 349, and it's a width. Okay, and you can see the height. Now we can measure the height now. So that's also around 349. That means around 350 micrometer. Okay, so simply you can press shift and K. So this will be erased. Okay, now this is the core area, but we have to allocate some space for the power lines. Okay, so for that first we have to make our floor plan in proper manner. So I'm going to select that floor plan, specify floor plan, and you can see here you have to give the location, or you have to allocate some space for the power lines. So I'm giving 30 micrometer width for the power lines. 30. Okay, so it will be surrounded by the core, this power lines. Okay, so I have assigned the size of the power lines around the core. So here, now you can measure this spaces will be allocated for the power line. So now you can measure that it will be around 30 micrometer. 30 micrometer. Okay. So now I am going to add the power rings here. Okay. So in this particular place where which we have already allotted. So now I am going to add power planning, add ring. So we have to select the nets for that, ground and GND. Okay, selected. Now we have to assign the width. So this already we know it is having around 30 micrometers. In between that we have to add two power lines. One is VDD and another one is source. So we can do one thing. So 10 micrometer for one power line. Okay, width of one power line will be 10 micrometer. So I'm assigning that 10 micrometer. Okay, so 10 micrometer, and the spacing will be 5. Okay, I will show you that. So 5 micrometers spacing, and this should be in center. Okay, so I'm giving like this. I'm selecting this center, giving OK. See now I will measure the width of this power line for better understanding. See here, this is 10 micrometer. Okay, in between this you have 5 micrometer. Okay, and this will be offset in center. Okay, so you will have 2.5 here and 2.5 in this location. Okay, so we have successfully assigned the power lines. Okay, now this is not enough because the transistors will be placed in the center of, or randomly it will be distributed, so you can't able to access the power directly like this. It is difficult, so you have to add an intermediate strips for that. Okay, so we are going to add an intermediate strip. So again, going to power menu, power planning, and add strip. So you can see here we are going to add some strips. Okay, so for ground and VDD, okay, you have to select the nets, and see here we have already given the width for this particular VDD and ground as 10 micrometer, but intermediate strips it is not necessary to give that much of width because it won't carry that much of current. So you can simply give half of this or a quarter of this like that. So I am just providing 0. Sorry, not 0.3, 3 micrometer. So this is 10 and I given 3 micrometer, and spacing, okay, I'm going to give 1.5 microns. Okay, 1.5 microns, and see I'm planning to place around 8 to 10 strips in between this vertically. Okay, so I'm going to select that strips. Okay, so here around 8 strips. Okay, so that's enough, you can give. Okay, but if you are feeling this particular strips are unnecessary, you can simply click on this. See here, this is the selection tool. You can click on this and simply you can press on delete key. Okay, so because that strips are unnecessary, because this transistor can directly access the power from this particular two lines. Okay, so that is unnecessary, so I have deleted that. Okay, and now everything okay. Okay, and but horizontally some more strips if we are providing it would be better. Okay, so what I'm going to do is selecting this route, special route, and selecting those two nets and giving OK. Okay, and simply I'm routing that. See here, so VDD, so this will be VDD and this is the ground. Okay, this is VDD and this is VDD and this is ground. Okay, so a particular transistor can easily access the power from these two lines. So transistors will be placed here, so it easily can access. Okay, so a drain and source can be properly and easily we can connect into this particular power lines, and the power can be easily accessed. Okay, now we have made everything clearly. Okay, so now we are going to place the standard cells. Okay, so for that place standard cells and press OK. So here you can see the results. So now it's added. You can simply press on this fit window so that it will redraw the structure. Okay, so you can get a layout. Okay, it's a placed standard cells. Now you can see that, these are the port. You can see here this is the port and it's labeled. See here, it's a multiplied output Z. You can see the code, and so this particular top module is having 4 inputs with clock. So Z is the output, so it is having 32 bits. Okay, we are using a single precision floating point arithmetic, so it's having around 32 bits. So these are the inputs. So direction is coming like this. Okay, and outputs. Okay, so this in this tutorial we have compiled the code by using cadence RTL compiler, and also we have generated synthesized Verilog code for 180 nanometer technology library, TSMC 180 nanometer technology, and synthesized code we have imported in cadence RTL compiler, and we have generated layout. Okay, and we have performed placement, standard cell placement and routing we have performed, and we have generated the layout. Thank you for watching.